Okay, so we are doing more now, more examples from section 5.6, integration by parts. And this is a very famous type example, the one I'm showing you here. Let me give you a moment to copy the example down. Okay, and then we'll proceed. So this problem, how do we know that integration by parts is going to be helpful? Well, we have in this problem, the integrand is the product of two functions that are very different. There's no connection between e to the negative theta and the cosine of 2 theta. It's not like you can take the derivative of one of those functions and get the other function. Okay, there's no direct relationship. So like substitution, no direct relationship between those two functions in terms of like one function being the derivative of the other. So we can't use substitution here. We have to use integration by parts. Now, as you remember, integration by parts, the formula is integral of u dv equals u v minus the integral of v du. Okay, that's the formula for integration by parts. And so, we want to know what this integral is going to be. What's the antiderivative going to be? And so, on the left here, we're starting out with the integral of u dv. And the question is now, so, again, this is like we're starting out on the left side of our integration by parts formula. Question is, what's u going to be? And what's dv going to be? We have to decide. Now, sometimes sometimes only one choice will work. And you can select u and dv, and if it doesn't work, if the integral isn't becoming easier to integrate, then you got to choose something else. In this case, what we're going to do is we're going to let u equal the cosine of 2 theta and dv equal e to the negative theta d theta. That's going to be our choice for u and dv. And it turns out that, well, all right, so let me write the formula down again for integration by parts. I'll write it up here on the top right-hand corner. And remember, on the right side, click zoom. On the right side of your screen, there should be a zoom feature to blow up the image. How many are using that? How many are using that zoom feature in Blackboard here? Okay, Samuel is, and very good. Hold on, I gotta. Right, Rayet is, Leping is. I gotta get it used to. Oh, okay, Jacob and Ryan. Good, excellent. Okay, so
Professor.
Yes, Sophie.
So, in deciding what to make equal to U and V, is there like a a thought process that goes in your mind specifically, like besides just trial and error? You said some work and then some.
Well,
Is there a way I could like more accurately, guess which, what would work?
it turns out in this case that if we had let u equal e to the negative theta and dv equal cosine theta 2 cosine 2 theta d theta, that would also work. Sometimes it doesn't matter, but what you want to, if you do an integration by parts, when you do your assignment of u and your assignment of dv, if when you after you do it one iteration of it, you get you're going to get an integral, right? You're going to get an integral when you apply the formula. If that integral is more complicated than the integral that you start with, then you know you're doing something wrong, because you'll never get it. So whatever you get has to be easier than what you started with.
Okay.
That's my best guidance. And a lot of this, when you get enough practice, you'll develop a feel for this.
Sounds good.
Good question. So integration by parts is integral of u dv equals uv minus integral of v du. Okay. Now remember, when u is equal to cosine of 2 theta, du d theta is going to equal negative sine of 2 theta times 2 by the chain rule. Okay, and therefore du would just equal negative 2 sine of 2 theta d theta. I mean, that's how we get this. That's how I get this here. Okay, that's how I get that. And then for the other part, if I mean, maybe this will help think of it like this. If you have, maybe I'll put this in purple. You have dv equals e to the negative theta d theta. If you integrate both sides, there's a 1 there, a 1 right here. You're going to get v equals, okay, what's the antiderivative of e to the negative theta? It's going to be e to the negative theta over negative 1. Okay, that's what it's going to be. And of course there's plus a constant there, but you don't worry about that here. And that's how you get the v equals negative e to the negative theta. So one part of it you're doing the derivative, the other part of it you're doing the antiderivative. And then of course here is, here is u v. Well, actually, I guess I got it as v. Hold on. Hold on here. One moment. Okay, so I guess I have it as v. Sorry. I have it here as v times u. Well, that's the same as u times v, minus the integral of v du. Okay, well there's v here. Now hold on, let me just, oh wait, hold on. One moment, let me do it again here. One moment, Samuel, one moment. VU, and this here, this entire thing, hold on, the integral of u dv equals u v minus the integral of v du. So this here is v times du. And because you have two negatives, a negative times a negative is a positive. And that's, you know, like you have a positive there, right? And so, yeah, question, Samuel?
Oh, never mind. Okay.
Okay. So what happened here now is we did the integration by parts. We did one iteration of it, and you know, we end up with this integral here. Now this integral, would you rate that as harder than the original integral, easier than the original integral, or just kind of like equally hard? What do you think? I agree, Jacob. Equally hard. Yeah, that's right. That's right. So, what we're going to do here, I mean, normally what we would love is to have an integral, to have this integral here be like easier, so that we can eventually, you know, integrate and get the answer. But what we're going to do is we're going to do a little trick here, and keep in mind this entire right-hand side here, this entire right-hand side, I'm denoting by I. So the integral I, which was my, you know, that's the integral. You know, you might wonder, Dr. Duty, why are you calling this integral I? I'm going to show you why. What I'm going to do is I'm going to do integration by parts again. Okay, this time I'm going to let u equal sine of 2 theta, and then the remaining part of the integrand, e to the negative d theta, that's just going to be dv. So it turns out then that du will equal 2 cosine 2 theta d theta, and v will equal negative e to the negative theta. And so I'm applying integration by parts twice here. I'm applying it twice. And when I do that, I wind up with this expression down here. Okay, please let me know if you have any questions on that. Yes, Jacob.
Sorry, I think I missed how it became +2 and then the integral.
Oh, let's see. So okay. So here. Okay, I have VU, and then here, this whole part here is minus, hold on, the integral of u dv equals uv minus the integral of v du. Okay, well, v is negative e to the negative theta. Du is 2 cosine 2 theta d theta, but I'm subtracting that, so that's how I'm going to get a positive. I'm subtracting a negative.
Okay.
And that's why I get a positive there.
Okay, thank you.
Sure, no problem. All right. Are there any other good questions on how I got how that we're here?
Yeah, so for me, the same part but in front. So how did you get the negative e, negative theta, all that?
So for uh, okay, so like let me just put a little box here. So looking here, dv is e to the negative theta d theta. I'm going to integrate both sides. Okay. And on the left, actually, hold on for just, hold on. One moment. One moment here. All right, what I want to do here, I don't know if I can do it. I don't know, is it going to let me do it? What I want to do, I need a little more space here. All right, hang on, let me do this again. Okay, so you're focused here, right? Right, Marcus? You're focused here.
No, I'm focused for the last I equals all that. So I understand the second part is the UV minus VDU, but what about the part in front of it?
Can you use your like arrow to point to the area that that's of concern to you?
Yeah.
Like you,
So this whole thing. Can you see that?
yep, yep.
Okay, yeah, that.
Okay, okay. So, well, this here is this here, right? I'm just bringing that down.
Mm-hmm.
And then the rest of it is this part, minus 2 times something. That's that minus 2 there. And then here's the integration by parts that I did on the integral. V and U, V and U, minus the integral of U dV. This whole part here, let's see, is minus the integral of V du, where here's V and here's du. Because I'm doing integration by parts on this integral. I did integration by parts the first time, and I still have this, I have an integral. So I'm going to do integration by parts on that integral again, and that's going to then get me this new integration by parts right here. Is that okay?
Yeah, okay, I think I got it. Thank you.
Okay, sure. Well, it turns out that something interesting happened. On the second integration by parts that we did, the integral that we got, okay, the integral that we got here is, isn't that the same integral we started with? So I'm going to distribute the negative 2 to both of these terms. And so my integral I is going to equal negative e to the negative theta cosine 2 theta plus 2e to the negative theta sine 2 theta minus 4 times the integral, or minus 4 times I. So we are trying to solve for I, right? We're trying to solve for our integral. I mean, based on this equation here, can I solve for that integral? Can I solve for I?
No, it's a loop.
No.
Are you sure? Think about algebra.
Can you add like terms or something?
What do you want to add? I like that.
Would you add the negative e to the negative theta and the
Well, I want to get the I on one side of the
oh,
equation.
you would add it. Oh, okay, so you would add the 4 to the other side.
That's right.
Okay.
That's
4 on the
right. Good, Samuel. Good. So let me, if I may, let me go to the next page. So, I mean, here's what we have. Here's what we have, and I mean, I'm trying to solve for the integral I, so I can add 4 times that integral to both sides. It's an equation, right? I mean, this is an equal sign here. It's an equation. So if I add 4i to both sides, then on the left side, I'm going to get 5i. These I terms on the right will cancel out, and I'm left with this on the right side. And so my integral is going to equal then negative 1/5 e negative theta cosine 2 theta plus 2/5 e to the negative theta sine 2 theta. And then we have our constant of integration because it's an indefinite integral. And so here we are. We have our answer. So it turns out that the loop helped us. The loop was a good thing. How many think that's pretty cool? All right. Jacob, Samuel, Maria, Leping. Okay, yeah. Do you think this could be something you see on your exam, first exam? Problem like this? Samuel says definitely. Well, put it this way, it's likely. All right. A question, yes, yes.
Would you prefer if we kept it as everything over 5 or the way you wrote it out?
I'm flexible on that, Samuel. WebAssign should accept either answer. What you have here, this function, you have basically a decaying exponential function times a oscillating function. So you have a dampening function times an oscillating function. And that kind of thing can come up like with mass spring systems. Okay, and I don't know, do any of you have to take differential equations like Math 282? Okay, Jacob does, and you and Abhidhar, and so yeah, this is pretty important application here. All right, I want to do a few more problems. Are there any other good questions before we move on? Okay. So, you know, let's look at another problem. Let's look at a few more problems here. Okay, here's one. Let me give you a moment to copy this one down. Okay, and let me see up here. There's the integration by parts formula. So we have to decide what's u going to be and what's dv going to be. And we don't have, well, Samuel, you're almost right. You're almost right. Why don't we let the entire arctangent function be equal to u and let dx equal dv? Let's see if that works. I mean, we have to try something. All right, so here we go. I'm letting u equal the arctangent of x to the negative first. I mean, 1 over x is x to the negative first. And I'm letting dv equals dx. If dv equals dx, then v equals x. On the left side, okay, I have to get what du is. So I'm going to find the derivative of u with respect to x. And on the right-hand side here, what property am I applying here when I take the derivative? I mean, I get 1 over a denominator of 1 plus x to the negative first squared, then times negative x to the negative second. What property for differentiation did we use there that you learned in calculus 1? What is that?
Chain rule?
Good. That's right. Chain rule. It's just the chain rule. We know the derivative. I mean, we know that the derivative of the hold on here. I mean, we know that the derivative of the arctangent of x is 1 over 1 plus x squared. So the derivative of the arctangent of x to the negative first would be equal to this expression. But then, so your outer function is the arctangent. The inner function is x to the negative first. The derivative of x to the negative first is right here, negative x to the negative second power. Okay, and it's kind of complicated, that right-hand side. So I'm gonna now unwrap the exponents and write those terms as fractions. Okay, and so that gets us down to here. Okay, and I'm going to multiply top and bottom of this fraction by x squared. So then du will equal -1 times, on the top, du will equal the fraction -1 over x squared plus 1. Because remember, you're distributing the x squared. To those two terms. And so now we have the integration by parts. V times u in this case, minus the integral of minus the integral of v du. Here's v, here's du. Now the limits do not change when you do integration by parts. For substitution, limits will change. You get new limits. But for integration by parts, the limits remain the same, and I just have them where they belong, right? That gets us here. Now, please let me know if you have any questions. These are a little bit harder, these integration by parts problems. So, I always think about you when you're doing your homework, and I want you to do your homework honestly. I don't want you to use any websites or anything. I want you to do the concepts, work them out, but I do recognize that in students, whenever you do homework, there's always challenges. So I try to do a variety of problems to help you. Okay. You still have you're going to have new problems, but I think this problem is one that's good to talk about. Jacob agrees.
I had a question.
Oh, question, Jacob? Yep.
I just wanted to clarify. You said that when we're doing integration with substitution, that's when we need to change the
Okay.
limits, but with integration by parts, you don't change the limits.
Well, we can move to the next page then, if there are no questions.
Oh, can you hear me?
We can move to the next page, but if you have a question, please feel free to ask.
Sorry, Professor. I think my mic turned off. Can you hear me?
Jacob, I think your volume is very low.
Okay, is that better? Can you hear me now?
Oh, I can hear you now, Jacob.
Okay, sorry. Yeah, I was asking a question. Sorry about that.
Okay.
So I just wanted to clarify. You said that with integration by substitution, that's when you need to change the limits, but with integration by parts, you don't need to change the limits.
That's correct.
Okay, cool.
That's
Thank
right. Okay. All right. Well, now hopefully we can do this. Certainly we can certainly evaluate this, and I think we're going to be able to evaluate this integral too.
Professor, real quick. So
Yes.
here, let me get the pointer. So over here, you erased the markups, but basically you did the x squared. You multiplied it on the numerator and the denominator.
That's exactly right.
Yeah. So would it also just be okay to just multiply this instead, and then like the -1 goes to the top, and then the x squared goes to the bottom? Would it be okay to do that instead?
put it this way. So if you can go from here to here,
Hmm.
I mean, I have to put in, Marcus, I have to put in this step here
Hmm.
in order to you know, get there, you know, in order to get down here. But you know, if you can recognize that, I mean, that's okay.
Hmm.
That's okay.
Okay, thank you.
All right, you're welcome. Okay, well, let's proceed on then. Let's proceed on. So, all right, here's our integral. And you notice I call it integral I. Now, you know, turned out the last example we did, it was very handy calling the integral I, you know. I just by convention call my integral I. So of course, here's the, you know, the evaluation of x times the arctangent of 1 over x at root 3 and 1 is done here. Done here. You put in the root 3, you put in the 1. Okay. And again, you know, all right, triangles, you know, we have our well-known triangles, the 30, 60, 90 degree triangle and the 45, 45, 90 degree right triangle. They're both right triangles. So you've seen them before. It might have been a little while, okay, but you've seen them before. This Calculus 2 course is going to bring together all the math that you learned. So it turns out that since the tangent of pi over 6, or 30 degrees, is equal to 1 over root 3, tangent, you know, well, I can, I guess, put this, the tangent of 30 degrees is equal to 1 over root 3, because tangent is opposite over adjacent. So at 30 degrees, the opposite side is 1, and the adjacent side is root 3. So the tangent of 30 degrees does equal 1 over root 3. So therefore, the arctangent of 1 over root 3 is pi over 6. Similarly, the tangent of 1, or I should say the tangent of 45 degrees is equal to 1, which is like 1 over 1. So the arctangent of 1 is going to equal pi over 4. Okay. So this problem has a lot of parts to it. A lot of parts, but hopefully it's making good sense. Now for this integral on the right here, this integral here, substitution will work. Let u equals x squared plus 1. Turns out then a half du will equal x dx. And so, and here now you change the limits, right? So the 2 there is because, you know, u equals x squared plus 1. So hold on here. 1 squared plus 1 is equal to 2. And the 4, that comes from root 3 squared. The x limit was root 3 on top. So if you take root 3 squared plus 1, you'll get 4. See how beautiful that is? Okay, and I am recording this. This is all in the recording, but I I think it's very good to take notes in your notebook. I think it's good. How many find that writing things down helps you remember things, or understand things, I should say. Jacob, Marcus, Audra, Baraka, Maria, Sean, a lot of people. Michelle, excellent. Tal, yeah, I mean, Jazi, sure. Sophie, absolutely. Baraka, absolutely. So, okay. Well, now the antiderivative of 1 over u is just the log of the absolute value of u. And our integral, our definite integral, this is the final answer then. Root 3 over 6 pi minus pi over 4 plus 1/2 times the log of 2. That is the exact answer. Oops. Okay. Are there any questions at all? How many think this is pretty beautiful stuff that you're learning? Okay, Jacob's liking it. And Sean. Samuel and Abhidara. Excellent. Hold on here. There was a chat thing. Oh, Ryan asked, thank you, Christopher. Why does it turn into the log of the absolute value of u? That's just the antiderivative. The antiderivative of 1 over u is the log of the absolute value of u. That's one of the rules, like in Calculus 1. In the textbook in section 5.3, and your ebook has, like, we're going to cover chapters 5 through 8, but your ebook also includes chapters, 1 through 5. So like section 5.3 is in your ebook. If you look at section 5.3, there's a table of common antiderivatives, and this is one of them. How many recall seeing that maybe in Calculus 1? The antiderivative of 1 over u is the log of the absolute value of u. I'm sure you okay, Sean, and okay, a lot of you. Great.
I have a question, Professor, about the last step.
Oh, okay. Let's take a look. This part right here, right?
Yeah. Where does the 4 over 2 come from?
Well, do you remember? Now I'll say WebAssign would take this answer. WebAssign would take that answer. But remember, if you have the log of a divided by b, and of course we're assuming a and b are greater than 0, that equals the log of a minus the log of b. How many, do you recall that from your pre-calculus days?
Why do we have a over b?
I'm sorry?
Why do we have a over b? Is that just what
Well, it's one of the log rules.
Absolute value of u is?
It's if you have the log of a quotient. So we write the quotient as a over b, a fraction. That equals the log of a minus the log of b. And so we applied that rule. We applied that rule right here, so that I could write the log of 4 minus the log of 2 as the log of 4 over 2, which is the log of 2. It's just an application of one of your log rules. You have other log rules too. Do you remember what the log of a to the bth power is?
Isn't that Isn't that b log of log a?
That's right. Now, we didn't use that rule here, but that's another log rule.
So you're just applying. Okay, so it's just one of the. Okay, so it's just.
That's right. We're just applying the log rule to make
Got
the
it.
final answer, to make it just look a little nicer.
All right, thank you.
You're welcome. You're welcome. All right, I'd like to do one more example with you, and then I think we'll take a little break. I'll give you some time to work on the new 5.6 exercises. I have to take the password off, of course.
Actually, wait, one more thing.
Yeah.
So the ln4 minus ln2 over ln4 over 2, that's, wait a minute. Oh, that becomes 1/2 and then times. Oh, okay, got it. Okay, never mind.
Okay, very good. Very good. Tal, you have a question?
Yeah, I have a quick question regarding the online assignments. So are we going to have access to old assignments, or are you taking them off? Because they make for good practice.
Oh, during class, I take access off.
Okay.
And I'll tell you one reason I do that. You're here, right, listening to the lecture. You're learning. And I don't think it's fair that students that are learning during class, then you're learning, but you're not working on the homework. But then maybe another student might I'll just I won't attend the class, but I'll work on my homework during class. I don't want that. I don't want that. It's really in part because I want students to listen to the lecture. But I know you're listening to the lecture and you're not working on homework during class. But I also don't want a student who maybe is going to just not attend class and work on homework during class. I just don't like that idea, And but everything, I've deactivated the assignments, but I will activate them. They'll all be activated after class, and you haven't lost anything. Everything that you got right, Tal, your scores on those like that you've done so far for your assignments, you haven't lost anything.
Right, but I just want to make sure, as in even outside of class, whether they'll still be available in the future after their due date.
Oh yes, absolutely.
Okay,
Absolutely. Now sometimes during class time I'll deactivate them, but I'll then activate them again. Absolutely.
Okay, great. Thank you.
You're welcome. You're welcome. Nathan, how are you doing? You have a question?
Yeah, so just to clarify, that third term on the very bottom line, that's a bracket, not a fraction, right?
This, hold on here, the third term.
Yeah, so you're saying ln of 4
yeah,
minus ln of 2 can be
these are
also
parentheses.
okay,
These are
but that's not like a fraction.
No, it's not a fraction. No, this is the log of the absolute value of 4 over the absolute value of 2.
Okay.
That's
So they're just a
very
weird confused. I thought the whole thing was one fraction.
No. Good question. And this is why I really, this is really why, learning and the lecture is important. And I want to encourage everybody to be here, and you are. This is excellent. Perfect attendance today. I want to keep going. Okay, let's keep going here. Another example. Now, this is something in differential equations you'll see. Okay, let me give you a moment to copy that down. Okay, so what are we going to do with this problem? What makes this problem hard, class? What makes this problem hard? Samuel?
Interestingly enough, that was the wrong button that I pressed. But there's only one term in this in this problem. As in, there's no u. As in, there's no u in a DV. There's only.
But we've dealt with that kind of thing before. Remember, we had we've had a kind of problem where we had one function plus like dx, and we've managed to use integration by parts. But I understand what you're saying. It makes it a little more interesting. But I think
the x is in the power.
Rayon's suggesting that square root of x there. I mean, what do we really want this to be? What would be much nicer than e to the square root of x? What would be much nicer to have?
E to the x.
Yeah, that's right, Sophie, e to the x. So what we're going to do here is we're going to actually do a substitution, and then we're going to do integration by parts. Okay, so in other words, what I'm trying to say is we have to simplify this integral. Okay, so we're going to make a substitution first. We're going to let u equal x to the half power, which is the square root of x. So let's go to the next page. Okay, so u equals the square root of x, which is x to the half power. And I'm going to convert this integral here. I'm going to be converting this integral to an integral with respect to the variable u. So, okay, well, let's see. So we're gonna let u equal x to the half power. Du dx would equal 1/2 times x to the negative half power then. Now, let's think for a moment. So I'm replacing e to the square root of x with e to the u. And what I have left is the dx. I've got to write dx in terms of the variable u. All right, well, I know that du is 1/2 times x to the negative 1/2 dx. And I want to get the dx by itself. I want to get the dx alone. So what if I multiplied both sides of this equation here by x to the half power? I mean, it's an equation. If I multiply on the left by x to the half power, I multiply on the right by x to the half power. And why do I choose x to the half power? Well, it turns out that, you know, I mean, x to the negative half times x to the positive half is x to the 0th power. What does x to the 0th power equal, class?
1.
1.
1. Oh, okay. So that gets me the dx alone. That's right. Excellent participation, everybody. This is great. This is great. Is it helpful? I don't know if is it helpful when I mark things with the marker on the sheet, on the page? How many is that helping? Okay, good. I was wondering about that. Wonderful. I And this is one of the advantages of having, like doing it this way. It's fine. It's fine. So, okay, dx is then 2u du. And so now I have my new integral. So I made this substitution. Letting u equals square root of x. And I get then this new integral. Can we integrate this new integral? The integral from 1 to 2 of 2e to the u du. Can we integrate that?
Yes.
We can. Excellent. Excellent. What technique are we going to use?
Integration by parts.
That's right. That's right.
Can I ask a quick question?
Sure, Maria.
So in your orange, where it said x to the half du, you substituted in the fact that u was x to the half, and that's where you got u du equals half dx?
Oh,
Is that
that's
correct?
right. That's right. The x to the 1/2 was equal to u. That's exactly right.
Okay, thank you.
Yeah. You're welcome. Okay. All right. Are we ready to go to the next page? Notice, of course, we have new u limits. Okay, very good. Okay. Well, all right. So here's our integral. I'll bring the 2 out front. And what I'm going to do, what makes things a little bit complicated here is, the normal integration by parts formula is integral of u dv equals uv minus integral of v du. Right? That's the normal integration by parts formula. Well, I had my integral is, hold on here, one moment. Okay, hold on. All right, my integral is with respect to u. So it would be easier if I chose different variables for my integration by parts. So instead of integral of u dv, why don't I do integral of w dv? That way I'm like not using the u like twice and get all confused, So here's the original integration by parts formula. If instead of u I have a w, integral of w dv equals wv minus the integral of v dw. So then I'm going to let w equals u, and I'm going to let dv equals e to the u du. And then the integration by parts, the iteration, I'm going to get this here. And then, well, okay, the antiderivative of e to the u is just e to the u. And we work it out, and we get 2e squared. And that's the exact answer. That's the exact answer. Okay, that is the like the best answer. Okay, so it turns out then that the integral from 1 to 4, hold on here, try this again. The integral of 1 to 4 of e to the square root of x dx equals 2 times e squared. Let's see, Nicole says if you let the answer this way, that's okay, Nicole. That's okay. It's, let me see though, hold on, yeah, WebAssign would accept this answer. I just simplified it a little bit. Okay, you're welcome. Now I'll make a comment, actually, up here. It'll address one of the questions that you all had. So what if, like here, what if instead of letting w equals u and dv equals e to the u du, what if I let w equals e to the u? Okay, and I let dv equal u du. Well, then I'd have dw equals e to the u du. But what would v equal? What would v equal, class? If I let dv equals u du here, what would v equal?
V would just be, oh, V would be just u.
What's the antiderivative of u?
Oh, u squared over 2.
Right, u squared over 2. So when you do your integration by parts, right, you're gonna get this. Okay, you're gonna get, you know, the integral would equal, and I have to just kind of write it this way. I'm sorry, it's e to the u times u squared over 2 minus the integral of u squared over 2 times e to the u du. Right? That would be your integral I there. If you were to integration by parts, let w equal e to the uth power and dv equals u du, this would be what you would get for your integration by parts. Now, are we happy with that? Are we happy? In other words, was this choice a good choice?
No,
Why not, Maria? You're right. Why not?
it just makes it more complicated and you'd have to do more work.
And what's the more complicated part? I agree with you. It is more complicated. Why? What's like? Could you be more specific?
Well, now you would have to do another integration by parts because you have two separate entities that don't have any correlation to each other, right?
Well, and also, let me ask you this. We started out with the integral of the integral of u times e to the u du. When we did the integration by parts using this assignment of w and dv, we get an integral with u squared over 2 times e to the u du. Is that more complicated than the integral we started with?
Yes.
It is. And so it's just going to get worse and worse and worse. You see? So that's a sign then that if you, when you do integration by parts, if you get an integral that's like harder than what you started with, then you know it's not going to work. And so you have to go back. So like some of you in the homework might do this. You might make these assignments, w equals e to the u dv equals u du, and you end up with this. But then you know that that's not going to work. So then you go back and say, oh, well, let me try to let w equals u instead, and dv equals e to the u du. You see? So that's a sign of you know, and really a lot of this is you know, you just practice, getting experience. That's where you know, where you'll learn. You know. All right. Are there any questions on that? All right. So then this is our answer here. All right. Give me one moment here. One moment, class. Okay, I'll stop the recording then.